I'm Patricia Matthews. This is Raphael, Marcelo, and Rebecca, and we are CardioCarry. Our goal is to increase the viability of the human heart fit for transplant from 4 to 8 hours. The current way for doing this is to just use a standard ice cooler. And while this is cheap and easy to produce, it's not as effective as it could be because it's not uniform nor rapid enough. So, University of California, Berkeley has found a way around this by developing a device that keeps the heart at near perfect physiological state. We're taking a different route. We're going to cool the heart internally as well as externally. By optimizing the flow rate and temperature of the coolant through the heart, we should be able to reduce thermal stresses, which are a main factor to the decay of tissue. Our results should be fairly accurate since we have researched the material properties of myocardial tissue, which is the muscle tissue of the heart, as well as certain plastics that emulate these properties.
Alright, the primary objective of our project is to construct a synthetic heart that would mimic the real human heart. This includes the thermal conductivity of the human heart, the specific heat, and the density, the size and geometry as well. We also want to use these same principles in designing a 3D CAD model for the drawing so that we could run computer simulations of the flow of the coolant within the heart, and as well as showing the distribution of temperature within the heart, and ultimately constructing a see-through and shatterproof container that will be used as the pumping apparatus so that the coolant be pumped through the heart. As I mentioned earlier, the synthetic heart we're constructing needs to have the same material properties of a human heart, which makes the actual selection of the polymer very important. We need to test different materials and different substances to try to get the right mix. We also need to make sure that the synthetic heart has the chambers inside to mimic the atriums of a human heart, and as well as the wall thickness so that the temperature distribution mimics a real heart. And then our apparatus also needs to act as a monitoring system to monitor the temperature and the stress loading on the heart. So several temperature probes and stress loads would be added into the apparatus.
Alright, bearing in mind that CAD simulations take longer and become less reliable, and prototype production becomes more costly and more complicated with the more features that you add, we started with very simple rectangular box shapes. The flow was obviously completely wrong on the first one, so we tried to model the wall thicknesses more accurately. We more accurately placed the valve placements, and we filleted all of the edges, but the flow still wasn't behaving the way we hoped. So this is a 3D rendering of the model that we actually designed in CAD. It most accurately represents the characteristics of a heart, and it shouldn't pose any insurmountable, it's going to be more difficult, but it's not going to be impossible to produce. We also hope that our polymer can be see-through so that we can watch the flow. We have 3 options for manufacturing it: lost wax casting, reverse silicone molding, and cavity mold printing. All of these involve 3D printing and filling some kind of mold with our chosen polymer.
This is a proof of concept project. Before we can begin transporting human hearts, we need to prove that this can work, and we need to develop a physical model and a CAD model with which we can use to study how it should behave and predict how it will behave. We need to see very clear convergence with the results if we can draw any conclusions from this, and preferably as much similarity between the two as possible. There will be differences because of the physical plastic model, you're going to have more deformation than on the CAD model, but if we can see the same trends, we can make accurate predictions as to how it will behave. There are several ethical and global considerations for a project like this one. The truth of the matter is there has been much testing on tissue, such as kidney tissue, liver tissue, and even brain tissue for preservation. We're more focused with the heart and how that'll behave. So we're going to make a very concerted effort to make sure that all the sources are properly documented and we give credit where it is due. Also, since the purpose of this project is to extend how long a heart will last, that means that more regions will be open to receiving such a heart in time for transplant. These regions may have different languages, labeling methods, and units, which we will also take into account. Again, it's just stress, this is a global project because if we can double the amount of time that a heart can last, we can almost double the amount of people that could be saved. Any questions?
Very good. In pumping those coolant through the heart, what risk are we running to contaminate the heart?
You want this one, Marcelo?
Yeah, we would need to, well, currently, under Dr. Dulikovic, he has a TA working on a coolant that would be non-toxic. So that's a primary issue. We don't want to damage the heart chemically, because then it would be useless to the donor. So that's something we need to look into. The coolants we're probably going to be doing primary testing on would be water with ice and simple mixtures like those.
We're mostly worried about thermal stresses and mechanical stresses. We're working, like you said, with a grad student who's doing the chemical side of the coolant.
No, but you can't ignore the biomedical, so.
We're not. It's because it's so early in the research. We're liaisoning with him. And he's
Well, address that in some way, shape, or form, so you can demonstrate to our IAB folks that you're quite the expert. You fully understand what all the issues are. All the issues and the tissues.
Yeah, questions?
All right, I have no other questions. Very good work.
Neither.
Thank you.
Thank you very
All right.
much.